Evening everybody, the name is Ben and I'm here to talk a little about the properties and tables related to thermodynamics. Much of the data we use here is related to water, but the ideas apply to a wide range of substances, assuming the system is in quasi-equilibrium. This is a 3D graph of the states of water in equilibrium. In this class, the answer to every water-based question is somewhere on the surface. If it is not on the surface, then it is not equilibrium. But my goal here isn't to tell you what it is, but to rationalize it, and show you how anyone could come up with these tables. There are three things you want in this graph: temperature, pressure, and specific volume. Specific volume being how many cubic meters per kilogram. These three forming the axes of our graph. Let's start with the easiest of the three, the temperature-pressure table. We know that water boils at 100 C, but at lower pressures, for example at higher elevations, the temperature is lower. So lower pressures mean lower boiling points. We also know that water freezes at 0 C. You may know that water expands when it freezes, so pushing harder on it should keep it a liquid during lower temperatures. In reality, it takes a lot of pressure for even a little change, so we'll make this slope just a little off from vertical. Now, these lines aren't exactly linear like this. They do have a bit of a curve to them. But while imagining these things, it's helpful to not sweat the details. This graph does continue to pressure and temperatures that explain ice to vapor, but we aren't going to need that. But let's put it on, just so there's a separation between solid and vapor. In fact, this graph is incredibly incomplete, but water gets pretty weird at high pressures and we aren't going to use that anyways. The temperature and specific volume and the pressure and specific volume graphs will be a little different. Let's assume you have liquid water in a container with a massive lid that you begin to heat up. As it heats, the liquid water expands. At some point it begins to turn to vapor. Now this is important. It takes a lot of energy to turn a liquid into a vapor, and in order for this to be in equilibrium, the lid can't be moving. For the lid not to move, the pressure on the outside should equal the pressure on the inside, and that is true during a whole experiment. But wait, you're showing it move, I hear you screaming. Yes, but very slowly. So slowly it's almost as if it's not moving, and the error is negligible. That's the point of quasi-equilibrium. So as more energy gets put into the water, that energy gets stolen by a molecule to jump into the vapor phase. But now there's a higher pressure under the lid, so the lid rises to equalize the pressure. Notice the volume goes up, so it occupies more cubic meters per kilogram. We call this an arrest because the boiling stops the temperature from rising until all the liquid has vaporized, at which point the temperature may rise again. Now let's do it again, but at a higher pressure. We know at a higher pressure it takes higher temperature to boil it. Then we know that liquid at a higher temperature would have expanded to a greater volume. But at some point it will begin to boil and it will follow the same rules. Except this time we know that the vapor is compressible. Thus, specific volume is lower. Notice the temperature affects the specific volume of the liquid, and the pressure affects the specific volume of the vapor. Liquids are said to be incompressible, so pressure doesn't affect the volume of the liquid. And while it is not the temperature that decides the volume of the vapor, but rather it is the temperature that gives the vapor more kinetic energy. More energy means more pressure, and it is the difference in the pressures that decide the volume. If we map out all the points where it begins to boil and begins to liquefy, we find a slope like this. Now you might ask, what happens if we keep raising the pressure to the point where there's no arrest line? We'll get back to that. Now there is also this line here that separates the solid and liquid states. We do not need it for the class, but it will help relate these graphs to the 3D version. Our final graph, the pressure-specific volume, is similar to the temperature one, except here, we're pushing on the lid to adjust the pressure inside the container. This one's a bit of a doozy and is easier to explain going from vapor to liquid. As you compress the vapor, it takes up less and less volume, but at some point it begins to condense. Compressing more won't change the pressure, but will change the vapor into a liquid, making it more compact. When it's all liquid, pressure may rise again. Trying again with a higher temperature, it'll follow the same rules. It'll stay vaporous until a higher pressure. Higher pressure means smaller specific volume for the vapor. Higher temperature means the liquid has thermally expanded more. Connect all the points together again and it looks similar. If you really lower the temperature, you get into more lines that again we don't need to know, but it does help build a complete table. These lines don't cut through the curve, they actually pass in front of the curve. This can happen because these 2D tables are actually part of a 3D table. We're finally ready to glue the axes of these graphs together to get a 3D version. You can see the peaks and corners of all the graphs line up perfectly. Now Ben, that is all fine and dandy, but you haven't even mentioned tables. Very true, and the script is getting pretty long for a 5-minute project. If you plot the points on these tables, you can make these: a pressure temperature, a temperature-specific volume, and a pressure-specific volume graph. Mix them into the 3D graph, and you get this. These saturation tables are points on this arch in the center. If we're told the pressure can't change, it slices the graph at the pressure value. Depending what pressure it is, we can find the specific volume or vice versa. Same holds true if we're told the temperature can't change. If you need a point that is not on the arch, we look at the compressed or the superheated tables. They describe the lines coming out the sides of the arch. To wrap things up, take a peek at the end of the saturation tables. You'll notice the specific volume of the liquid is the same as the vapor. When something floats on water, it is because that thing is less dense than the water. If it sinks, it's because it's more dense. We know specific volume is nothing more than the inverse of the density. By the end of the tables, the liquid and the vapor have the same densities, and thus, the liquid freely floats around in the vapor. This is the critical point, and it is equal to the peak of that arch. All of this still holds true for the tables given for the R134A. And that's it. Armed with this knowledge, you can tackle most basic thermodynamics problems. Thanks for watching.